everyone. My name is Tingting Chen, and I'm from DTU. And I'm sorry for you that you still have one more presentation, and I will try my best to run through my presentation as soon as possible. And today I'm going to present deep learning applications in frozen crystal growth production, and I'm the one who collaborates with the TopSU. And I will start with introducing the background about the frozen crystal growth as well as the deep learning, and also I will present the two case studies of deep learning applications. And wafer is no doubt the backbone of the electronic industry, and wafer fabrication is starting with crystal growth, which is to convert polysilicon to single crystal ingot by solidifying silicon from its melt. And frozen crystal growth is one of the crystal growth methods. And because of the contactless heater, so it can allows for manufacturing silicon crystal with very low impurities, especially low oxygen concentration. And the typical applications are wind turbine and solar cell and electric vehicles. And however, there's still a challenge that is to keep the frozen process oxygen free, because oxygen is kind of a contamination of the frozen process. And it happens often that we observe there is an abnormal phenomenon on polysilicon surface. So in the normal process, if we look at the image from the vision system, the polysilicon surface is normally with a homogeneous intensity. However, however we observe an abnormal phenomenon is that because of the interaction of the oxide, we observe something abnormal on the polysilicon, and actually it's oxide layer formed on the polysilicon surface. And because I mentioned that oxygen is a contamination, so it will have the potential to threaten the product quality, and also it will threaten the use. So our objective is to achieve oxide-free process, and we focus on two aspects. The first one is focus on what? That is to identify the oxide layer automatically. And the second step is to diagnose why it will form the oxide layer, and also to diagnose how do we improve the process. And then because so as Christian mentioned that the main goal is to reduce the operation cost, and also there is some limitation whenever involving human. So that's why we turn to deep learning. And actually deep learning is a subset of machine learning, and it's a kind of neural networks with deeper layers. And the difference between the machine learning and deep learning is that the deep learning can free us from pre-processing, and also from feature extraction. So with such a powerful tools, we can apply in several stages. So for example, like to know what stage, that is to so for example, to identify the object, and also we can use it for know-how, that is to review the correlation between the defects and process variables, and also we can use it for to know when, that is to forecast variables, and also we can use it for know-how that can provide some decision making for us. And then here comes our first case study. So we focus on know what, that is to identify the oxide layer. So our goal is to achieve is to develop an automatic detector for different oxide types with different characteristics. And so we can leverage a convolutional neural network to output the oxide types. However, as you may know that convolutional neural network requires a large amount of the label data. And also this requires a large label cost in the labeling. So we leverage transfer learning, and the main core of transfer learning is to transfer the knowledge of the model, which is already pre-trained on the large data set, and with the transfer learning, it can allow us to directly train on the small data set, and also it can achieve the relatively high performance. So that's why we leverage transfer learning, and the results showing that using pre-trained model can outperform the model's training from the scratch. And also, as Marvin mentioned, that it's not sufficient to convince the company to use such a model because it's kind of a black box. So we try to inspect model behavior by kind of a saliency-based method that is GregCAN, which can help us to know whether the model has already learned, really learned. And with this tool, it can kind of point out which features are interested for the outputs. And here we can see that the the left-hand side is the original images, and the right-hand side is the kind of the heat map that model that the model is more interested. So here we can see that the model can somehow locate the oxide layer, which means that it's actually learning. And with this oxide layer detector, we can generate many tags from the production, and we can correlate the oxide types with other data source, and we observe that the oxide layer is highly relevant with water concentration within the chamber. Of course, we can directly monitor the water concentration by using the moisture sensor, but the problem is that the moisture sensor is very expensive, and currently Topsil only has one moisture sensor, and it costs much. So it's not really realistic to install the moisture sensor on every frozen machines. And also, there is still a further need to diagnose why there is a high water concentration. So here comes the second case study, and the goal is to predict the water concentration within the chamber based on the existing data from more accessible sensors. And here we utilize the 3 different types of data. So for example, the image data from the vision system, and the tabular data, which records the process type and machine ID, and also some material data. And also we have some time series data from the log data. And then the goal is to try to develop a model which can output a water concentration, so that we can replace so that we can replace the physical sensor. And here comes 2 problems. The first problem, that we have different data structures, and also the second problem is that how can we jointly learn from different data. And here our method is try to use a different feature extractor. So for example, for the image data, we can leverage convolutional neural network, and for the tabular data, it's easier because we can directly use NLP. And for the time series data, we can take advantage of recurrent neural network to extract the features. And then we can use a transformer to jointly learn these features. Transformer is a typical model architecture that can automatically capture the variables dependencies with self-attention mechanism. So in brief, it can automatically pay more attention to more important features. So that's why I use it, and I use it for the water concentration prediction. And the results is here. So here you can see that the prediction is more or less following the trend of the actual water concentration. And of course, this is not enough. We still need to to inspect model interpretability to know which features are more relevant, so that we can kind of have more understanding about what kind of features will cause high water concentration. So currently, I'm still working in the model interpretability. That is to utilize the attention waves to try to find some explanations, and also I'm also working with another tool that can directly generate feature importance. So, in summary, today I present the two case studies to show that deep learning can be applied and also can help us to optimize the process somehow. Yeah. So that's my presentation, and that's all from my side.
Perfect.